Space exploration is no longer just a dream of the distant future. It's rapidly becoming a reality, with plans to establish human habitats on the Moon, Mars, and beyond. The question of how to sustain life in such harsh environments is more pressing than ever. Among the most significant challenges is managing the extreme temperature variations that these extraterrestrial environments present. On the Moon, for instance, temperatures can swing by an astonishing 500 degrees Fahrenheit. During the lunar day, which lasts about 2 Earth weeks, the surface temperature can reach a scorching 250 degrees Celsius, 121 degrees Celsius. But when the sun sets, the temperature plummets to 208 degrees Celsius, 133 degrees Celsius. These drastic changes pose a serious threat to any human-made structure, making temperature regulation a critical aspect of designing space habitats. Maintaining a stable, livable temperature inside a space habitat in these conditions is no small feat. Traditional heating and cooling systems, as we know them on Earth, would require enormous amounts of energy to function effectively in space. This energy demand would not only be costly, but also unsustainable for long-term missions. So how can we create a space habitat that can maintain a comfortable temperature without relying on energy-intensive systems? The answer may lie in the innovative use of phase change materials, or PCMs. PCMs are not a new concept. They've been used in various industries for decades. These materials work by absorbing and releasing thermal energy as they change phases, for example, from solid to liquid and back again. This process allows them to store and release heat over time, providing a form of passive temperature control. When integrated into the design of a space habitat, PCMs could act as a thermal buffer, absorbing excess heat during the lunar day and releasing it during the frigid lunar night. To understand how PCMs work, let's take a closer look at the science behind them. Phase change materials operate on the principle of latent heat. When a material changes its physical state, say from solid to liquid, it absorbs a significant amount of heat without a corresponding rise in temperature. This absorbed heat is known as latent heat, and it's what allows PCMs to regulate temperature so effectively. For example, water, a common PCM, absorbs heat as it melts from ice into liquid water, and it releases that heat when it freezes back into ice. In space habitats, specialized PCMs are designed to operate at specific temperatures that are conducive to human life. One such material is in-octadecane, a paraffin that melts at around 82 grams, 28 degrees 6, just above room temperature. This makes it ideal for maintaining a comfortable indoor climate. Imagine a space habitat where the walls are lined with N-octadecane. As the habitat absorbs heat from the harsh lunar day, the N-octadecane inside the walls melts, storing the heat. When the temperature drops at night, the material solidifies, releasing the stored heat and keeping the interior warm. This passive heating and cooling system could significantly reduce the energy needed to maintain a stable environment for astronauts. But the potential of PCMs goes beyond simple temperature control. These materials could also be used to enhance the energy efficiency of space habitats in other ways. For instance, PCMs could be incorporated into thermal batteries, which store excess energy generated by solar panels during the day and release it at night when the sun is no longer shining. This would allow habitats to maintain power without relying on additional energy sources, which are often scarce and expensive in space. However, the application of PCMs in space habitats is not without its challenges. One of the biggest obstacles is the sheer amount of material required to regulate the temperature of a large habitat. Current estimates suggest that several tons of PCMs would be needed to provide adequate temperature control for a habitat the size of the International Space Station. Transporting such large quantities of material to space is prohibitively expensive with today's launch costs, making this approach less feasible for the initial stages of space colonization. Moreover, integrating PCMs with other construction materials, such as lunar regolith, presents additional challenges. Lunar regolith, the loose fragmented material covering the Moon's surface, is an abundant resource that could be used to construct habitats directly on the lunar surface. However, combining regolith with PCMs in a way that maximizes their thermal properties while maintaining structural integrity is a complex engineering problem that researchers are still working to solve. Another factor to consider is the reflectivity of the habitat's outer surface, which plays a crucial role in how much solar radiation the habitat absorbs. The effectiveness of PCMs is partly dependent on the amount of heat absorbed by the habitat's exterior. If the surface is too reflective, it may not absorb enough heat for the PCMs to function optimally. Conversely, if the surface absorbs too much heat, it could overwhelm the PCMs, causing them to melt too quickly and lose their ability to regulate temperature effectively. Additionally, the location of the habitat and the specific conditions of the local environment must be taken into account. For example, a habitat on the Moon's equator would experience more extreme temperature variations than one near the poles, where temperatures are more stable. This means that the type and quantity of PCMs used in the habitat's design would need to be tailored to the specific conditions of its location. Despite these challenges, the potential benefits of using PCMs in space habitats are immense. As materials science continues to advance, researchers are developing new types of PCMs that are more efficient and cost-effective than those currently available. For instance, recent study ISRU could significantly reduce the cost and logistical challenges associated with transporting PCMs from Earth to space. By producing PCMs on-site, space habitats could be built and maintained more sustainably, paving the way for long-term human presence on the Moon, Mars, and beyond. In addition to their use in space habitats, PCMs have the potential to revolutionize other aspects of space exploration. For example, they could be used to regulate the temperature of spacesuits, spacecraft, and even food storage systems. By providing a reliable, energy-efficient means of temperature control, PCMs could enhance the safety and comfort of astronauts on long-duration missions, reducing the risk of heat-related illnesses and improving overall mission performance. Looking ahead, the development of advanced PCMs could play a key role in enabling the next generation of space exploration. As we prepare to return to the Moon and venture further into the solar system, the ability to create stable, livable environments in harsh, unpredictable conditions will be critical. PCMs offer a promising solution to this challenge, providing a means of passive temperature regulation that is both effective and sustainable. In conclusion, the application of phase-change materials in space habitats represents a significant step forward in the quest to establish a human presence beyond Earth. While there are still many challenges to overcome, the potential benefits of PCMs are clear. As research continues and technology advances, these materials could become a cornerstone of space habitat design, making the dream of living and working in space a reality. The future of space exploration is bright, and PCMs are poised to play a crucial role in making it possible. So, what do you think? Could these innovative materials be the key to unlocking the secrets of the cosmos and paving the way for humanity's expansion into the stars? The possibilities are as vast as the universe itself, and the journey is just beginning.